Heisey Alliance. There's Dr. and
Thank you. Thank you, everyone. Okay, our study is some interesting. We just found possible trace to investigate the evolution of dark energies with the CO, Heisey CO, and the C2 galaxies. There's some relations we found. Okay, so the story is taken from this. We all know this in cosmology pi is dark energies, big portions coming from this previous observations with supernova type ones. And also proposed is our universe is accelerating expansions. Yeah. So this is one question that said, if okay, the theoretical thing say that expansions caused by the dark energies. Okay, and supernovas indeed strong evidence, given strong evidence, theoretical consistent with the observation. Yeah. So this is one question: does dark energy change at different epochs of the universe? If a dark energy causes the accelerating expansion of the universe, yeah. So, but this is a disadvantage to use supernova type ones because you can see if these two pictures is supernova rays will decline as the ratio becomes larger. And this is a theoretical work that if we want to know the evolutions or different or degeneracy of the dark energies, we need to go to the high ratio regions. But in current time, the current observation, the ratio of supernova type 1 is still in 1.4, even 1.9. So it's not too higher to get to the higher ratio regions. Yeah. So fortunately, well, in this 20 years, within this 20 years, 7-millimeter galaxies, 7-millimeter observations are giving me more and more higher ratio galaxies. It even go to touch to ratio 8. So there also the relation, luminosity to line with the correlation has been proposed in CO emission line. So these two pictures give you this relations that indeed exist between the luminosity and the line width. Okay, but you can see this data here is quite inhomogeneous because it's a mix, a different transition of molecular. Yeah. So in our work, and then okay, you can see this in this data. So all are in the higher ratio regions. Different is the ratios greater than 1. So if you want to give more confirmations and strong evidence, this relation indeed exists in these 7-millimeter observations. We need more data. So this is our work. We touch to the extension of our ratio region into the lower ratio in CO and C2, and this is the source of the data coming in the FCRO around Spitzer, Herschel, and even for the C2, currently we have data from ALMA. So this is our selections criteria. We followed some previous work. We selecting the galaxies inclination is larger than 30 degrees to involve the higher uncertainties in the inclination correlation. Yeah. So these numbers we selected, the 46 and even the 57s. Yeah. So this is a flow. We're doing the analysis. We confirm. We calculate the line luminosity, follow these numbers, and the distance we used on CDM models to decide the luminosity distance. And the corrections for inclination, correction for gravitational length, because some of the high galaxies they are deformations by the foreground galaxies. So we need to consider the gravitational lensings to transfer the observational luminosity to the intrinsic one. So then we're doing the linear regression, so with the ideal codes here, and to investigating the stronger how significant the relation between the luminosity and the light is. So this is our results. For this one is for C2, this is for CO molecular 120, and this is for C2, and this is data. The red dots means low Z. The blue ones means high Z one. So the relations is formed like this way, and you can see this result, passive feed result in here. The alpha is 0 point, beta is just slow, and we change and we confirm the significance by the calculating Spearman coefficients. Even we put sorry, I did not put down the p-values. I should put down p-value here. But in these numbers, although this is a little bit smaller, but we can check that the relations, the correlation between the luminosity and the light is indeed significant correlation. Yeah. And we can also see the slopes, that they are consistent with the 1 sigmas. And for this bands, one sigma uncertainty bands, they are covers largely. So in here, we have a conclusion that these two relations, low Z and high Z ones, shows no significant sign of a ratio evolution. This is an assumption, okay? But in the data, they show this doing follow this way, yeah. So with this is no significant sign of a ratio of evolution of relations. We can do something in cosmology. For example, we can decide the distance of the highest galaxies. We extending the Hubble diagram into the very high ratio regions with the CO and the C2 data. You can see this is calibrate with the low Z one, low Z galaxy. For this black data is showing the supernova. And you can see this red dot. The red dot is showing the pulse galaxy of gravitational wave event 170870. It's a very low ratio here for this curiosity. So we want to use this 1 point to constrain the parameter, cosmological parameter in two models, WCDM and CBL model. In here, in this WCDM models, we assume that the equation of the state of the dark energy is the constant. No evolution here, but it's a constant. So you can see if we use this higher ratio of galaxy here in constraints, the contour become the shape right way, right to here. But in the W0 is the equation of the state of dark energy. But they are still inconsistent. Yeah, it's maybe indicated there's a low Z with combined with the supernovas galaxies. Supernovas data, the universe is doing the more matter-dominant behavior. For the CPLs, we investigate the evolution of dark energy. So you can see this. We combine with the IZ1, IZ data, become the lower. But there's become the WA means evolution factors of equation of the dark energies. So it means it's also strong evidence that we can use this IZ galaxy to investigate the equation evolution of the dark energies. But for the red dots, although there's only one single dot, single data here, it becomes just a little bit larger. It's also showing the worthies. Maybe we can use the GW events in cosmology constraints. So this is starting here. Thank you.
Okay, any questions?
So you concentrate on the WW by sheet observation of the sheet 2.
Yes.
So, so the dispersion is very large. So in this diagram, so they are not. It's caused by program.
And you mean the scatter?
It's such that it's very large.
Scatter is also largest. I think maybe this coming from calibrations,
Yeah.
the distant calibrations, and there's also the limitations in our sample size.
Okay.
Yeah. So it's our also we hope future surveys we get much more data so that the relation become tighter, or even the calibration, distant calibration can much more enhance. Also, there's a scatter will be shrink.
Oh,
Yeah, yeah.
thank you.
So any more question? Okay, then let's move on to the next